Good day. Today we are starting with chapter 13. For this chapter you will be needing tables, namely table A6 and table A10. Please have that ready. The focus in this chapter is on frequency tables. The data in this chapter are counts, not measurements. The variables are categorized. And we're working, therefore, with discrete data, with a theoretical background, that which we did in chapter 3. Now let's just have a look again at the difference between continuous and categorical data. For continuous data, we have measurements. The variables that we observe can be measured on a continuous scale. And chapter 9 to 12 that we've done this semester are all based on continuous data. The procedures were all based on probability distributions of continuous random variables from chapter 4. However, categorical data, which we'll discuss in this chapter, are based on counts. Variables observed fall in one of several different categories. Chapter 13 is based on categorical data, and the procedures based in this chapter is based on probability distributions of discrete random variables. And that's very important to remember. From now on, your first question should be, what is the nature of my data? Is it discrete or continuous? And then you decide on what to do, which techniques to use further. The first part that we're going to consider is the goodness of fit tests and categorical data analysis, but with emphasis on goodness of fit tests first. So we're going, some examples of problems that will be addressed in this chapter are the following. Is a die balanced? Or is the mobile market share in 2016 the same as in 2014, or in 2017 the same as in 2014? Is there a relation between gender and occurrence of accidents? These are all questions that we'll answer. The first two fall in the category of goodness of fit tests. In other words, to answer the question of is the die balanced, or is the mobile market share the same as the previous year or a previous year, that fall into the goodness of fit tests section. And the data analysis is more focused on, is there a relation between two categorical variables such as gender and occurrence of accidents. So the hypothesis regarding proportions that we're going to look at is an extension of what you've seen before. In chapter 9.3 and 10.4, you considered hypotheses regarding one or two proportions. There's the summary of your single sample test for the equality of a proportion to a specific value. And there's the summary of your procedure when you compare two proportions from two independent samples. Now, the theory for one sample and the two sample case was based on the normal approximation to the binomial distribution. Now, the procedures in this chapter are going to be based on a generalization of the binomial experiment. And this generalization is called the so-called multinomial experiment, where in the case of a binomial experiment, we have two outcomes, success and failure. In a multinomial experiment case, the outcomes can be any one of k different categories. It can be, for example, age that has been categorized, or it can be eye color, or it can be car color, or brand of car, their make, and so on. The null hypothesis in the binomial experiment that you're familiar with is that P is equal to a specific value, which immediately implies that Q will be equal to 1 minus P0. So you actually need to specify only P. However, the null hypothesis in the multinomial experiment requires that you specify what is the value of P1, the probability of having an outcome in category 1, the probability of having an outcome in category 2, and the probability of having an outcome in category K. The alternative hypothesis for the binomial was just that the proportion of successes is not equal to the specified proportion. For the multinomial experiment, the alternative is that at least one of the proportions are not equal to the value specified for that specific category. Both cases consist of an experiment where we have n trials. The random variable that we were interested in the binomial case was the number of successes, which we can indicate with the number in the first category, denoted with a capital letter N1, and then the number of failures would be N minus N1. But we only consider the number of successes, in other words, in category 1. While on the other hand, with a multinomial experiment, we consider the number observed, or we look at the number in each category. We don't know beforehand what it's going to be, so that's our random variable. So we have K categories that we are considering. What do we observe? We observe cell frequencies in both cases. The number of successes in the case of the binomial experiment, we know that N1 is the number of successes. It's a number in category 1, and the number in category 2 then is the total minus the number of successes. The same principle is used for the multinomial experiment, but there we will have N1 for category 1, N2 for category 2, up to Nk for category K. Of course, the total number of trials being N in both cases means that your number of successes and number of failures add up to N. And likewise, here the number of observed frequencies in your first category plus the second category up to the K category also adds up to N, but it is also equal to the sum of your expected frequencies in each cell. Your expected frequency in each cell, in the case of the binomial, is the well-known expression for the binomial, n times the expected proportion of successes. Here it's going to be the expected frequency is going to be the total, meaning the total number of trials, times the probability associated under the null hypothesis with each category. So note that the binomial experiment is just a multinomial experiment if K is equal to 2. Of course, these proportions will also add up to 1, and all these frequencies need to add up to N. So the last category is also being determined by what's in the first K minus 1 categories, just like what's in the second category is determined by the first category. In this chapter, we're going to look at two basic procedures. We're going to look at one-way frequency tables, which has one row or one column, with J columns or categories, or it can be the other way around as well. But let's consider, first of all, one row with J columns, or it can be one column with J rows as well. But let's stick to one row, J columns. Then we're going to look at goodness of fit tests, and we're going to consider three different scenarios where the probabilities are known, and you will see that then we have K minus 1 degrees of freedom. The number of categories minus 1, and that relates to my earlier remark which said what happens in your K category depends on what happens in the preceding K minus 1 categories, because they all add up to N. But then we're also going to look at goodness of fit tests where the probabilities are to be calculated and is not known from the start. And then we're going to look at scenarios where the probabilities are not just calculated, but they need to be estimated. And then you have K minus 1 degrees of freedom minus an additional M, referring to the number of parameters that will be, which we'll need to estimate. This is described in section 13.1 and 13.2, and I'll elaborate on this later. The second kind of problem that we'll discuss in this chapter is the so-called two-way frequency table. That's when you have I rows and J columns. So not only one row, but I rows. And then we're going to look at a test for homogeneity, and I'll elaborate on that later on as well, and a test for independence. This is described in section 13.3. So let's consider the goodness of fit tests first, where probabilities are known. Here we're going to consider tests when category probabilities are completely specified. Completely specified is very important. The other situation will be when category probabilities are functions of other parameters. That differentiates the second kind of problem. And when the underlying probabilities of the categorical probabilities are continuous. So we're not going to focus only on discrete distributions, but we're also going to look at continuous distributions. For example, we're going to look at a procedure to determine whether data is actually normally distributed, but by using a discrete approach to a continuous variable. Then we'll be looking as well at composite hypotheses, where we need to estimate parameters for discrete distributions or for continuous distributions in order to do the goodness of fit test. And then lastly, the contingency tables, the test for homogeneity, and the test for independence. And what we're going to do, first of all, is focus on the goodness of fit tests. This is sections 13.1 and 13.2. First of all, then, when category probabilities are completely specified. The first kind of goodness of fit test that we're looking at is where the probabilities are completely specified. So the binomial experiment, for example, with success and failure, we have a row total of n. There's x successes, n minus x failures. The binomial experiment, we have ni observed in the first category, n2 observed in the second category, and nk observed in the last category. So, according to our hypothesis, namely that the null hypothesis P0 is equal to a specific value, then we have that the expected value of a success is the total number of trials times the probability specified under the null hypothesis. Similarly, for the multinomial experiment, under the null hypothesis, for the multinomial experiment, we are saying that the first probability is equal to a specific value. The second probability is equal to a specific value. And this will be given. So the expected number in our first category will be the total number of trials times the expected probability times the probability specified for the first category. So that's n times p10 or n times p20. Like you have the expected value for a binomial under the null hypothesis in p0. Now, when will you reject the null hypothesis? You will reject the null hypothesis if your estimated proportion differs a lot from your supposed proportion. In other words, you will reject the null hypothesis if the observed frequency is much different to the expected frequency. In other words, if that difference is large. So the same will hold for the multinomial experiment. You will compare what you observe in the first category to what you expect in the first category. Compare what you observe in the second category to what you expect in the second category. And so on till you get to the kth category. Observed in the kth category compared to expected in the kth category. Now, in other words, the difference must be large. So by now you already know that we don't usually look at differences. We look at squared differences because otherwise the differences are going to cancel out the positive and negative differences. But the square difference between the observed frequency and the expected frequency is not sufficient as a test statistic in the case of the goodness of the test when category probabilities are completely specified. Why not? Consider the next scenario. We have a null hypothesis where we test whether P1 is equal to a specific value up to Pk being equal to a specific value. If the null hypothesis is true, we expect the frequency in the ith category to be equal to a number of trials times the proportion specified under the null hypothesis for the ith category. If the null hypothesis is true, they should be close, so the difference should be small, so the square difference should also be small. And if the null hypothesis is not true, the square difference should be large. But what happens if we only consider the squared deviation as a test statistic? Consider two possible scenarios in category I. If we have an expected frequency of 100, an observed frequency of 95 versus an expected frequency of 10 and an observed frequency of 5, and we only consider the square deviation, you can see that it's 100 minus 95, which is 5 squared, and that's 25. 10 minus 5 is 5 squared, that's also 25. So the square deviation is the same in both cases, but 95 is 5% less than expected. 95 minus the expected value expressed relative to 100, what you expected, while 5 minus 10 divided by 10, in other words, you look at the difference relative to what is expected. That's 50% less than expected, and that's a huge difference. So we have to take that into account. The size of the squared deviation is not enough. You have to take into account the expected frequency. And therefore, we look in our test statistic, we divide by the expected frequency as well. So it's an expression of relative deviation from the expected frequency. So in the first case, you can see that it's 0.25. And in the second case, it's 2.5. So this expression reflects the actual deviation from what we expect. It's like taking into account, if you compare a mean to a specific value, taking into account the variance. It's a similar idea that's being used here. So, if we use this as the base for our test statistic, we can proceed to the next. If we look at the square deviation for each one of the K categories, then this is our theorem. Provided that the expected frequency is at least 5 in each category, the variable chi-square, and look at this is the sum for each category of the deviation, the relative deviation of the expected frequency from the observed frequency. So you have observed minus expected squared divided by expected, summated over all cells. And then we say it has a chi-square distribution with k minus 1 degrees of freedom. The fact that the degrees of freedom is k minus 1 is a consequence of the restriction that the sum of all the observed frequencies is equal to the number of trials. So although there are k observed cell counts, once any k minus 1 are known, the remaining one is uniquely determined. That is, there are only k minus 1 freely determined cell counts, and thus k minus 1 degrees of freedom. Also note the requirement that each expected cell frequency must be at least 5. So we're back to the chi-square distribution, and as a reminder, table A.6, which gives upper tail probabilities, and if you want a left-sided critical value, you focus on the first number of columns in your table, and if you're looking for a right-sided critical value, you focus on the right side of the table, and down in the rows you get the degrees of freedom. So from this you can get the critical values and also the p-values, but there's a better way to get the p-values, and I will illustrate that later with an example. Now we know that we need to use the chi-square distribution, we know the test statistic, and therefore we can look at the complete procedure for testing the null hypothesis that the proportions in k categories are equal to specific values, and either the proportions or the frequencies must be known. So you have to determine beforehand what do you expect in terms of the cell probabilities in each category, or what do you expect in terms of the cell frequencies in each category. So a table for the calculation of the test statistic is very convenient. We always write down the observed frequencies. This will be given, the number of trials will give you the total, and then you get your expected frequencies. And what's important is to note that your expected frequency should add up to the same total, namely n. The number of trials will be given, you will see in an example. So there's your null hypothesis. Your alternative is that at least one of the proportions does not equal the specified value. Your test statistic value, look at, so you can add a row here. Look at N1 minus NP1 under the null hypothesis squared divided by NP10. And if you then add that all up, that will be your chi-square value. I will illustrate better in the next slide. Your rejection region is always a right-sided test, always an upper tail test. So you reject k minus 1 degrees of freedom for this particular procedure, all cells fully specified, all cell probabilities fully specified, and alpha. It's just an upper tailed test. So our next question, or first example, is a six-sided die balanced? The experiment consists of rolling a die 160 times. In other words, the number of trials in total is 160. In other words, we have a multinomial experiment. There's 6 possibilities. So k is equal to 6. And we want to test the null hypothesis that the die is balanced. Translated into symbols, that means that all my probabilities in each category is equal to 1 over 6, in other words 0.167. Now I've indicated that the table to solve this problem is very convenient. So here's my table. The calculations required to test the null hypothesis is then, there's our observed frequencies that's given. This will be given. My expected frequency in my first category is then 160 times what is specified for P1 under the null hypothesis. So it's 160 times 0.167, and that's 26.667. In the second category, the same thing. It's 160 times the probability for 2, and that gives you 26.667 as well. And the remainder will be the same because a balanced die means all sides have the same probability. Now we compare what we observed to what we expect if the die is balanced. So that's what we have there. My square is hidden there. It's 18 minus 26.667 squared divided by 26.667, and that's 2.8185. If you do the same thing in the second column, 30 minus 26.667 squared divided by 26.667 will give you 0.4158. Same for the third, fourth, fifth. Let's consider the sixth one as well. Observed 34 minus expected 26.667 squared divided by 26.667 gives you 2.0146. Now these cell values are called the chi-square cell values, the cell chi-square values. And the total here is your test statistic. It's a total of your cell chi-square values. You will see in SAS, it gives you the cell chi-square values as well. Note that your 26.667 times 6 is 160. These two must be the same. And now you can compare your observed test statistic to your critical value. Also, before I go to the last step in this procedure, note that all the expected frequencies are larger than 5. That was one of the requirements for the test procedure. So the complete test then. There's your null hypothesis, all probabilities being equal. That is implied by the fact that we want to test whether the die is balanced. So when it's balanced, we know that those probabilities must be 1 over 6. And the alternative then is that at least one of the probabilities is not equal to 1 over 6. Alpha 0.05 is given. We will reject the null hypothesis if the chi-square test statistic value is large enough. Under the null hypothesis, we've determined from our table that chi-square value is 7.4 rounded. And the test statistic value, which can be regarded as an observed value from a chi-square 5 distribution, 6 minus 1 is 5, where the critical value then is 11.07, we can conclude that we will reject the null hypothesis only if this chi-square value is larger than this, but it's not. So since it's not larger, the null hypothesis cannot be rejected, and we conclude that the sample evidence suggests that the die is balanced. Because the binomial distribution is a special case of the multinomial distribution when the number of categories is equal to 2, we have an equivalency between the chi-square test and the normal z-test, which we discussed in chapter 9.3. Take, for example, for the procedure that we've derived just now, the situation when we have only 2 categories. Then the null hypothesis can be stated as P1 is equal to P1 under the null hypothesis. But because the relation P2 is 1 minus P1 holds, the proportion of failures is equal to 1 minus the proportion of successes, and P2 under the null hypothesis therefore is equal to 1 minus P1 under the null hypothesis, the inclusion of P2 equal to P2 under the null hypothesis is redundant. So the alternative is just that P1 is not equal to P1 under the null hypothesis. So we can use a two-tailed z-test with test statistic z equal to the proportion of successes observed minus the proportion of successes expected divided by the square root of the variance of your proportion of successes observed. And that then yields the well-known z-test statistic. So the two procedures are completely equivalent. And that is because we know a squared standard normal variable is a chi-square variable with degrees of freedom equal to 1. And then your critical value for the z-test statistic squared will be the critical value for chi-square variable with degrees of freedom 1 and significance level alpha, so that a chi-square test will be rejected if it is the chi-square test statistic value is greater or equal to the critical chi-square value, if and only if the absolute value of your z-test statistic value is greater or equal to your z-critical value. If the alternative hypothesis is upper-tailed or lower-tailed, the chi-square test cannot be used. So one must then revert to an upper or lower-tailed z-test. But your two-sided hypothesis test, z-test, is equivalent to your chi-square test. In the last instance, just a reminder that you should not confuse statistical significance with practical significance. A computed chi-square that exceeds the critical value may be a result of a very large sample size. And then you have to be careful. There may not be practical differences between the hypothesized values and the true, under the null hypothesis and the true proportions, for example. So, for example, if you hypothesize that all the proportions are equal to a third, but the true proportions are 0.33, 34, and 33, a large value of the chi-square will indicate statistical significance. If your sample size is large enough, you will reject the null hypothesis. But before rejecting the null hypothesis, the estimated proportions should be examined to see whether they suggest a model different from that of the null hypothesis from a practical point of view. So you may find that your proportions differ significantly simply due to the size of the sample. But practically, there's not really a difference between 33, 34, and 33. But that will depend on the problem. It's just an emphasis on the fact that you can get statistical significance with a large enough sample size. Because this test becomes so sensitive that it will detect a difference between the sizes very easily. But it may not be a practical difference, only a statistical difference. More examples of goodness of fit tests when category probabilities are completely specified are given in example 13.1, so please work through that on your own. And your homework with questions that will be discussed, will be asked in ClickUp is exercise 3. A last remark is one that involves p-values for chi-square tests. You are familiar with table 8.6, which gives you the critical values, and you can get an interval for the p-value. But you can get the p-value more exact by looking at table 8.10, which gives you chi-squared curved tail areas. In other words, it's giving you the probability to the right of a specific calculated chi-square. So you can see you are given your degrees of freedom at the top in the row here, and here your p-values, upper tail areas are p-values. So for example, in our die example, we had a test statistic value of 7.4. The degrees of freedom for that test was 6 minus 1, in other words 5. So you can look at this column. And here you can see the values in the table are decreasing. 9.37, 9.23, 9. Smaller than 9.23. And that's associated with an upper tail area of larger than 0.1, which means your p-value is larger than 0.1. You will not reject the null hypothesis even on a 10% level of significance. So keep in mind that you can use this table to get the p-value more accurately.